So, hello everyone again. This is lecture 3 part 2 of alternating current. In the previous part of this lecture only we have started with a discussion regarding AC voltage applied to a series LCR circuit. So, let us begin our discussion regarding that topic only and then we can move forward. So, this is lecture 3 part 2 of alternating current. I am Sameer Lavankar. Let us begin our discussion. So, currently we are on the sixth topic, that is AC voltage applied to a series LCR circuit. Okay. So, let us continue the discussion directly. These all things are already being completed. Okay. So, now let us try to derive further regarding this topic. So, we have obtained till this point. Okay. So, what is the value of Vm? This value of Vm is nothing but equal to Im capital R whole square plus what is Vcm? Vcm is nothing but equal to Im into Xc, correct, and this will be nothing but Im into Xl whole square. Okay. Let us try to calculate, or let us try to take out Im square out. So, we will get nothing but equal to R square plus Xc minus Xl whole square, correct. In another sequence what we can write? We can write that Im squared is nothing but equal to Vm squared upon R square plus Xc minus Xl whole square, or we can write Im is nothing but equal to Vm upon under root of R square plus Xc minus Xl whole square. So, this is the equation, or this is the relation which we got for the value of Im. Please remember what is Im here. So, basically we in the starting of this solution we said that we need to calculate the value of I, which is basically in the form of I is equal to Im sin omega t plus phi, correct. So, this is the value of Im which we obtained till now. What is this value of Im? Im is basically equal to Vm upon under root of R square plus Xc minus Xl whole square. Okay. If you see correctly, every time when we are trying to understand the relations, let us start with the first relation. Okay. So, in AC voltage applied to a resistor, we understood that what is the, if the value of voltage every time was assumed as nothing but equal to V is equal to Vm sin omega t. Only the value was depending upon, for each of these individual devices, we either got value of we only got the value in difference of Im and phi. In the case of resistor, we got the value of Im is equal to Vm upon R, phi was 0. In the case of inductor, we got the value of Im as equal to Vm upon XL, where XL was equal to omega L and phi was nothing but minus phi by 2. In the case of capacitor, we got the same value of Im is equal to Vm upon Xc, where Xc was equal to 1 upon omega c, and we got the value of phi as plus pi by 2. In the similar case scenario, when we are trying to understand for series LCR circuit, again what we assumed? We assumed that V is equal to Vm sin omega t, and let us assume that using this phase diagram solution, the value of current is I is equal to Im sin omega t plus phi again. We just need the value of Im, we just need the value of phi. Now, using the derivation which we did currently using the phase diagram solution, we got the value of Im. We got the value of Im is nothing but equal to Vm by something. Vm by everything we are getting in denominator some sort of analogy to a resistance, correct. This time this resistance is nothing but equal to under root of R square plus Xc minus Xl whole square. As we analyze or defined a new terminology for Xl and Xc, again we will try to define a new terminology or new definition for this denominator. Okay. So, this denominator, or basically under root of R square plus Xc minus Xl whole square is nothing but called as Z, or denoted by Z, which is called as impedance. Please remember this very carefully. This is nothing but called as impedance. So, therefore, what is the final formula which we obtained for Im? Im is nothing but equal to Vm by capital Z. Okay. What is capital Z here? Capital Z is called as impedance, and this is nothing but analogous to your resistance. Fine. So, I think these all things are also completed. Now, let us try to understand the same thing for, okay. So, this is how the diagram is being created. So, basically what was happening here, if you see clearly, if you see very clearly what is the diagram, what is the relation we got that relation is nothing but equal to capital R square plus under root of xc minus xl whole square, correct. So, that same thing can be drawn in terms of a triangle also. So, basically what is the value of z, as this is 90 degrees. So, therefore, this z is nothing but by Pythagoras theorem equal to r square plus xc minus xl whole square under root, complete under root. Okay. So, using this diagram we can directly obtain the value of phi also. How can we obtain the value of phi? Using the trigonometric equations we can directly write that tan phi is nothing but equal to. So, in terms of this also we can obtain. So, if you see this triangle very carefully, what we can write using this triangle, what we can write? We can write tan phi is nothing but equal to V Cm minus V Lm. Please remember these are small v's upon V Rm, correct. Similarly, from this triangle what we can write? From this triangle we can again write tan phi is nothing but equal to capital Xc minus XL upon R. Okay. These both equations can be derived from one also. So, basically as we know the lengths of every value which is written here, what is VCM? VCM is nothing but equal to Im into Xc minus VLM is nothing but Im into XL upon VRM is nothing but Im into R. If you take Im out of each of them, we will finally obtain it is nothing but equal to Xc minus XL by R only. Okay. So, either you derive directly or either you go by this sequence, both time you will obtain the same result which is equal to Xc minus XL upon R. Okay. Fine. So, this is another equation. So, basically what were the two different thing which we required? We basically required I is nothing but equal to Im is nothing but equal to sine of omega t plus phi, correct. What is this value of Im? Im is nothing but equal to Vm by capital Z, where capital Z is impedance, and this tan phi or phi is basically equal to tan inverse of Xc minus XL upon capital R. Okay. So, I hope this complete solution is clear to you. This diagram is also called as impedance diagram. Okay, so this diagram is also called as impedance diagram. This is a right triangle with Z as its hypotenuse. Okay, that's all I needed to explain. Okay, let's start understanding whatever is written here. So, now these all things are simply logical based concepts which are written here. So, this is called as impedance diagram, which is a right triangle with Z as its hypotenuse, quite evident. So, basically this diagram is called as your impedance diagram. Now, if Xc is greater than XL, okay, so basically what was the value of phi we got? This phi is nothing but equal to tan inverse Xc minus XL upon capital R, correct. Now, okay. So, if Xc is greater than XL, that means that Xc minus XL is positive, therefore, phi will be positive and the circuit is predominantly capacitive. So, basically it depends upon whatever is written, which is the impedance, sorry, the reactance of capacitor or inductor is higher, whichever is higher we will try to say that that is predominantly that value. So, if it is capacitor, if Xc is greater than XL, we will say that it is the circuit is predominantly capacitive. If XL is greater than Xc, we will say that the circuit is predominantly inductive. Okay. So, only logical based definitions are given, nothing new here. So, if Xc is greater than XL, we will say that phi is positive and the circuit is predominantly capacitive. Consequently, the current in the circuit leads the source voltage, quite evident. So, we understood that for individual resistances also, in the case of individual capacitor, always the value of current which was obtained has had a greater value of this plus phi, positive phi. Also similarly, if you can see that as the formula which we obtained was nothing but equal to I is equal to Im sine of omega t plus phi, correct. So, anything, if we are getting any value of this phi which is positive quantity, then it is sure shot that every time the value of current will be ahead of this voltage. Okay. So, nothing new here. So, basically the current in the circuit leads the source voltage because the value of phi is some quantity which is positive. Okay. Next thing is if xc is less than xl, okay, only everything which is just said in the last 2 lines above will be opposite in the next 2 lines which is written here. So, if xc is less than xl, phi is negative, quite evident as you can see here, because xc minus xl will come out to be positive negative. Okay. So, if xc is less than xl, phi is negative and the circuit is predominantly inductive, right, similar quantity. So, if xl is greater than xc, we will say that the circuit is predominantly inductive. That thing being said, next thing is consequently the current in the circuit lags the source voltage, right, quite evident because phi is coming out to be negative. So, anything which is of negative sequence will always be lag behind the voltage. So, therefore, voltage will be ahead and the current will be behind. Fine. So, that thing being said, next thing is figure below shows the phasor diagram and the variation of V and I with omega t for the case xc greater than xl. Okay. So, I think this is the phasor diagram being shown here. So, whenever xc is greater than xl, you can clearly see that the current is leading the source voltage, and if it is leading the source voltage, it basically means that the peak of the current will come first, then the peak of the voltage will come after current. As you can see, the peak is coming, the peak for current is coming first and the value of peak for voltage is coming ahead. Please remember, this time the difference between the time required for the current peak and the voltage peak will not be pi by 2, it will be some another value, right, depending upon the value of xc and xl. For individual case, for individual capacitive case, it will be always pi by 2, but for series LCR circuit or any other circuit which is not individual sense, this value of the time difference between or the phase difference between the peak current and the peak voltage will not be pi by 2, will not be pi by 2. Okay. So, I guess these were all the concepts regarding phasor diagram solution, but now why we are if everything is known to us, why we are trying to understand it using another solution which is analytical solution. The reason for that is given in this slide. Okay. So, let us try to understand why we are trying to derive the complete equation or derive everything which we had just obtained using analytical solution also. Okay. So, now thus we have obtained the amplitude and the phase of current for a series LCR circuit using the technique of phasors, but this method of analyzing AC circuits suffers from certain disadvantages. Let us try to understand these disadvantages clearly. So, first the phasor diagram say nothing about the initial condition. So, this is the first disadvantage. So, we do not know basically what was the current, so at the starting point when this complete circuit was being closed, at that point what was the initial condition, was actually at actual position, was it starting at 0 position only or it was at some other location and so on. We assume something, but we do not know exact result of what was the initial condition. So, one can take any arbitrary, so this was the explanation for this. So, basically one can take any arbitrary value of t, say t1 as done throughout this chapter, and draw different phasors which show the relative angle between different phasors, but that is not the actual case of what it is starting at. Let us say it is starting at, let us say the current starts at this location, or basically the voltage starts at this location, but every time to ease out the process we are starting at this location which is the 0 value. What if it is starting from this location only? What if this is the actual initial condition? We do not know any idea, we do not have any idea or how to get it using phase diagram solution. Okay. Fine. So, one can take any arbitrary value of t, say t1 as done throughout this chapter, and draw different phasors which show the relative angle between different phasors. The solution so obtained is called a steady state solution, very important. Okay. So, please remember, this may also be asked in MCQ also, that which type of solution is being obtained using phasor diagram solution. Please remember that only a steady state solution is being obtained using a phasor diagram solution. Okay. This is not the general solution, general solution may be obtained using analytical solution. Okay. Additionally, we do not have a transient solution which exists even for V is equal to 0. So, if V is equal to 0, can we obtain actually what are the difference current which we obtained? Can we obtain something like this? Can we obtain some sort of EMF produced or so on, if we do not have voltage passing through it? So, we cannot use it using phasor diagram solution, but we may be possible using some further analysis. The general solution is the sum of the transient solution and the steady state solution. So, actual value, if the complete solution is to be required for a AC voltage applied to a series LCR circuit, we must need transient solution also, and we must need steady state solution also. Steady state solution can be obtained using phasor diagram solution, but transient solution cannot be obtained using this phasor diagram solution. Okay. After a sufficiently long time, the effects of transient solution die out and the behavior of the circuit is described as a steady state solution. Okay. So, different variations which happens actually in the starting, those all things are not being explained using phasor diagram solution. Basically, it refers to the time at which everything is being stabilized. Phasor diagram solution refers to those solutions which is being done after the steady state is achieved, and that is why it is known as steady state solution. Okay. So, then if that thing is being said, let us try to understand the analytical solution regarding this complete topic. So, let me start. So, first of all let me write the voltage equation again. Right. So, this is already known to us that the complete voltage using Kirchhoff's loop rule is only divided into 3 different devices. One was due to IR or resistor, then Q by C due to capacitor, and L di by dt due to your inductor. So, this is nothing but equal to Vm sin omega t, correct. Now, let us try to do some modifications in this LHS of this equation obtained. Okay. So, first of all what we do, we know that I is nothing but equal to dq by dt. Therefore, what is di by dt? Di by dt is nothing but equal to d by dt of dq by dt, that is nothing but equal to d2q by dt square. Okay. Now, let us try to obtain the equation number 1 in only and only terms of q. Let us try to modify the equation. So, what we will obtain? We will obtain in terms of di by dt, we can write it as equal to dtq by dt square, correct. In the term, in the place of I, what we can write? We can write it as equal to dq by dt into r, and in the place of q by c we can write q by c only. So, it is q by c which is nothing but equal to Vm sin of omega t, correct. Now, if you look at this equation very carefully, in class 11th you may have heard of a topic in waves oscillations, damped oscillator. So, this equation is similar to a damped oscillation. Equation is similar to a damped oscillator. Okay. So, first of all let us assume some solution. So, let us assume the solution as q is nothing but equal to qm sin of omega t plus some theta. Okay. So, therefore, dq by dt will be equal to qm omega cos of omega t plus theta, and d2q upon dt square is equal to minus qm omega square sin of omega t plus theta, correct. So, I think it is clear till now. Only an assumption is being made in which we are saying that q is equal to qm sin omega t plus theta, fine. So, after this here substituting all values obtained before, we can get the final solution for q value. Okay. So, let me stop it here only. I will try to substitute all those values and then we can finally obtain the true analytical solution for this series LCR circuit. Okay. So, that thing being said, I think that will be the ending of this concept also, and then we can move on to the next concept regarding resonance. Okay. So, let me stop it here. Thank you so much. So, thank you so much.